This is an example for calculating power from lecture 3.5. So in this problem, we have a 150-pound man that's running up a set of stairs that's 15 feet high. It takes him 4 seconds to do that, and we're asked to calculate the power generated by the man. It's not said, but generated by the man as he runs up the steps. Now, this problem statement isn't quite complete because we don't know information at 1 and 2. Basically, we don't know the man's kinetic energy or his velocities at 1 and 2. So I'm going to complete this problem by saying, let's assume that the velocity at the bottom of the steps, which would be v1, is equal to the velocity at the top of the steps, that's v2. That also then means that the kinetic energy is going to be equal at those 2 points. So that now is enough information that we can solve the problem. Okay, so I'm going to draw a free body diagram of the man running up the steps. Here's our man running up the steps. The force is acting on the man. There's an mg weight force. There's a normal force that's keeping the man on the step, so the reaction from the step. And there's also going to be a friction force F. If there was no friction force, then he would just slip and he would never go anywhere. So there has to be a friction force on the man's feet. Okay, so those are our 3 forces. We can put in a XY coordinate system also. And so now that we see these forces, we can ask which of these forces do work, because that's going to affect the power, our power calculation, because power is going to be work per time. So if we look at our forces, we can then ask which forces do work. So we can look at the friction force F and ask, does it do work? And if we look at the picture of the man, we can kind of draw in some friction forces along these steps where his feet are. And if he's not slipping, right, so let's assume also no slipping. Right, so he's not, and that's the normal situation when you're walking up steps. Hopefully your feet are not slipping. So if they're not slipping, then when his foot is in contact with the step, it's stationary. That friction force is not moving. It's stationary. And then as he steps onto a higher step, these friction forces that I've drawn here in red disappear. Maybe, as he goes up to the next 2 steps, these friction forces in green will appear at a different time, but these individual friction forces are not moving. They appear, they're stationary for a while until they disappear. And so because of that, the friction force does not move. And since work is defined as a force, or integral of a force over a distance, if there is no distance to move, then there is no work. So the friction force, the static friction force, does no work in this case. If we also look at the normal force, right, there's normal forces here on the man's feet. They're also not moving. They're at the location of his foot while he's stepping on the step, and as he steps off, they will disappear, but these individual normal forces don't move. As he steps up to the next 2 steps, these other, in green, these other normal forces will appear for some time, but they won't move during those times, and then they'll disappear, and he'll go up the steps and step on other steps. So we could say the same thing about N. The normal forces also do not move, and hence they do no work. Then we have mg. mg does do work. If we drew the mg over here on the picture of the man in green, this mg force on the man, it's moving with his center of mass as he moves up. So the mg does do work. So that's the only term that we can really calculate here, the only force on the free body diagram that does work. So to calculate our power, it's going to be a work divided by a time. So we need to figure out how much work the man is doing, divide that by the 4 seconds, and that tells us how much power the man is generating. So according to our work energy principle, we can say the kinetic energy at 1 plus the work that's done from 1 to the work that's done on the man from 1 to 2 is going to equal K2, kinetic energy at 2. But we know that K1 and K2 are equal to each other by our initial assumption. So these are equal and they cancel out. And so basically we're left with the work that's done on the man between 1 and 2 is 0. And we've already said that the mg does work, so there is going to be work on the man done by the mg force that's not 0. So there has to be another force, another work term that adds to that work of the mass, work of the gravity, so that it cancels out. And I'm going to say this is the work generated by the man. This is the work that the man is doing as he walks up the steps. And there is work being done inside the man's body. Muscles are contracting, so there's a tension in the muscles. Those are attached to bones that are moving, and so this tension in the muscles are moving as the bones, as he bends his legs, and so work is being done. There is a force that's moving over a distance. And so this is folded into this work generation term. So the work that's generated then is going to equal the negative the work of the mg force. And so this is something we can now calculate. It's going to be negative of the work done by the mass. The work done by gravity means the work done by gravity is actually going to be negative because the gravity force is down and the man is moving upwards, right? So he's moving up here, v. There's going to be some vy component to his velocity. So since he's moving up and the weight is force is down, this gives us a negative work. So we get another negative term here. So it's going to be negative the force, which is mg, times the distance, which is going to be this height. I'm going to say this height h here is 15 feet. So these negative signs will cancel. And so we're going to get that our work generated by the man is going to be positive mgh. So that's going to look like 150 pounds. That's his weight. That's mg, multiplied by the height, which is 15 feet. This works out to 2,250 foot-pounds. Right, so that's the work generated by the man. We can then also calculate the power generated by the man. It's going to be the work generated divided by the time. So it's going to be 2,250 foot-pounds divided by 4 seconds. And this works out to 563 foot-pounds per second. This is our answer. This is how much power the man generated as he ran up these steps in 4 seconds. And this is about 1 horsepower. 1 horsepower is 550 foot-pounds per second. So it's just a little bit more than 1 horsepower. Okay, so the key here was realizing that the friction and the normal forces do no work because they don't move. That's an important point. Okay, so we can do the second part of the problem. We're asked to figure out how long would a 100-watt light bulb have to burn in order to expend the same amount of energy, which was the work, the 2,250 foot-pounds. So here we can calculate our time by dividing that amount of work by the power of the light bulb. So our time then is going to equal our work, which is 2,250 foot-pounds. And we're going to divide that by the power. Power of the light bulb is 100 watts, but we're going to need to convert these units. And I know that 1 horsepower is 550 foot-pounds per second. I also know that it's 746 watts, right? So these are both, I'm basically dividing 1 horsepower by itself in different units. And when I do that, I can cancel watts, I can cancel feet, and cancel pounds, and I'm going to be left with seconds. So I get an answer here of 30.5 seconds. This is the answer to the second part.